This is so peculiar. Something is going on at 2.4 something on both sides, and then asymmetrically again here or there. And there is a little step here and here. The hidden noise of the floating point processor. Okay, I feel like making a prediction for this graph in terms of some function. That is, we need a lower bound, I guess, for this, and that we want to stay below. Let's see if we can figure that out. That is the maximum relative error in initial guess that results in 2 iterations. So for a value around here, say, it could be here or there. Just digital noise here, depends on the lower bits of this value, that we cannot go above, because if the relative error of the initial guess would be, say, here, and then we are going to have 3 iterations. But for some values also 3 iterations if it is here, but none of the values here, well, at least none, that's none that I calculated. That seems very unlikely. Yeah, so if we stay below this line, or even below this line, it is a little bit below that line here, then we are guaranteed to have 0, 1 or 2 iterations. 2 or less iterations. And I think it would be helpful to have a formula that draws a line that stays below this. And I'm gonna guess that that line is, well, let's begin with, I would say maybe more or less something divided by C naught. 1/10 divided by C naught, and then a little bit less. It's maybe even here actually. 0.075 divided by C naught. So add a function. I think I had to add a function anyway. Here. So let's make that a real function now. 0.75 divided by C naught. That probably will blow up. I don't want to divide by C naught if C naught is 0. Well, I don't want to divide by C naught if it gets larger than that. What is 0.2 divided by 0.2 divided by 0.075 is 2.666. I don't know, let's send something. Otherwise that, in this case I can return, let's say 0.5. Okay, so this is, C naught is small enough, then it becomes 0. Becomes a half. Just make it 1. That doesn't really matter very much. I don't have to think. Can add the other function as well, which is then the negative of that. Hello, flowery. No, it's going over it. Here it is pretty good. Now it's way too well. It's going up here, so let's wait until we are there. But it looks like not exactly what you want. This is too slow. Let's make it 10 times faster. We might miss this thing here, which is annoying. But to get in the neighborhood, let's make my step 10 times faster. What, 100 times faster. You call that 100 times faster? Not really. Yeah. I still have this one, even. Surprisingly enough. Chance of 1 in 100. I think I'm gonna stick with the 0.0. What is it? 0.075. Because then at C naught equals 1, we'll go through this point, which probably makes sense because of this one. Hey Alman, I'm using Cairo graphics, and Cairo window is what is actually drawing all this stuff. But it is based on the Cairo graphics library. I think I want to I have no idea what I want. I want to divide by less here to what about maybe the square root. The square root of C. Yeah, that's pretty nice. Now, normally I would have tweaked it to be closer to this one, but yeah, this one outlier, maybe, you know, Should not do that. And in fact, maybe we should. Well, I'm just rotating it around this point anyway. A little bit, you know. Like this distance is like 1.5. And this is way less. And it's getting closer and closer. Maybe eventually it's going through it. On the other hand, it is nice that where it matters, okay, where the relative error is already small, that we are really good at guessing this lower boundary here. Catches this point also very nicely. I mean, basically it's close here and close there. And here it's not as important, maybe. You would almost think that I have to shift it, right? But yeah, that can't be right. I'm going to draw it from -1 to 1. Wow, you see these? Sometimes there is a point that is on this line, more or less. Wow, I feel tempted to investigate what the hell is going on there. Yeah, no time for that. And this peak here is also very intriguing. I do think, however, that in this case I don't like it to be triangles. I want to just a single dot, really. Single dot. Maybe an open circle, even better. Let's begin with drawing a circle. That's my point style here. Filled shape, cross single. I think it's an ellipse. An ellipse is probably going to be a circle, and an unfilled is this one. So it's one more. 10. So this is 0, 10 down, 10. Yeah. I should have a dot in that list, really. Yeah, you saw the list. I didn't make a dot. I can add a dot. Let's just add a dot. Okay, so it's not going to be easy, I think, then, but dot. It's filled or not filled, right? I mean, maybe that's the nonsense. That I should be using something else at all. It's not a filled shape. Do I have... Oh, I just can't remember if I added something that is just a point or not. Is filled, get shape, line color, fill color, point. Wait, I have a point. No, this is the thing above. Yeah, you have to pass point style here. Do I call those things points, even though there I have a little shape. Position at corner should be ignored then as well, yes. Right. Now then we have to implement something that in the neighborhood of the other names. Let's pick one that is not too rhombus. Going to occur somewhere else, I mean, like what is this? Another. Hmm? Strange. Yeah, there's something like a next shape. I don't want to use I think this is intended to iterate automatically over different shapes, so you can different kinds of data keep them apart. You don't want to have a single dot suddenly in between there. So let's just leave that alone and look if we can fix it from here. But yeah, this is clearly that other enum. So how is this style then being filled from the thing that I just changed? Style. Shape style, I guess. Just this one. The shape. It ain't that easy. Well, I think I have to add something to this enum. It just draws a rectangle, ellipse, rectangle, rhombus, diamond, star, cross, plus, and then arrows. Might as well treat the dots as special as an arrow. Add it to the end. Okay, it's dot. How to make a single dot with Cairo. Because this is the center. Center coordinates, radius, and 2 angles. Like it says here. Center, radius, 2 angles. So the center is at a minus a half, minus a half, 0. Let's pretend that this is want to put the dot where the center is of this thing. So we have to move to, I suppose, that point. And then draw a single dot. No fill, maybe not even a stroke. Maybe we do. Yeah, we just have to make a rectangle. Maybe this. Draw a single line. Need to know how wide a 1 pixel is. This one goes through 0, 0. Seems more logical, right? Somehow I have to center in the middle. Right, how do I get a dot in here though? First of all, let's add it. I'm just going to add it at the end. Maybe we should call it pixel. No, call it dot. I have no idea which one it is, at corner or at center. I'm feeling total lost here. Clearly this thing must return dot, right? Style underscore, that is a member variable of the class shape. Shape has a member style, which is set here from the constructor. So it's the constructor of shape. And I'm trying to use the thing. By creating a point style. And a point style. Oh, this is the one I think then. Shape enum, right? Yep. So this should return, filled shape should return dot for this case. What? Oh, this is a shape enum. Ach, this is shape enum. So silly. Yeah, okay. So I'm just, by adding dot here, I'm changing all my programs that point to a certain thing to something else. Let's put it at the end. So I'm not doing that. One, two, three, four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I just pass 15 and then I get this dot, which is then the other enum, which I just added. So that should work. Except for one thing, of course. The size must be equal to 16 now. Yeah, that was this modulo here. Otherwise we would never have gotten dot. And then here we use 15. And then it's time, I think, to try to compile it. See what happens. My food is in the microwave and that stopped like 10 minutes ago. If not 20, so it's getting colder and colder. I'm going to get it. No, it's good enough for me. Those are definitely dots. Well, these now know if they are at the right position. Yeah. I have been trying to remove this dirt here. Is it dirt? No, because my mouse is hiding it. They go, oh, this is on my monitor. Looks like dirt. It wasn't. It's another piece of dirt, but it is not a confusing color. Okay, so let's put a dot 20 and then see if it exactly is on this cross here. I need to get my food. Short break. Give me a minute or two. Yeah, tasty, I hope. Hot. what? It's still hot. Oh. So that point is at 2, 0, but I wanted to see a bloody dot. That is not what I wanted. I have to see if the dot has the right coordinates. And let's move them out here. Hello, Clement. Come on, point, style, symbol up, dot. Hopefully it's the black one, the darker one. I think it is. Yeah, there is a dot here, and the dot is exactly in the center, right? I mean, if anything, if it is there at all, I think it's there. Yeah. Okay. So that works. Hello here. Yeah, let's just try not to divide by 0. No, it's not really very accurate here. Is it? Wouldn't it be nice if it just moved more along like it? how to do that. Hi, pretty function. I'm much better. I'm eating. I think I can eat everything again. I'm still eating something easy to digest right now. Tomorrow I will go completely crazy. No. Yeah, I had the microphone turned away. So yeah, anyone has any idea? This curve here, the black one, is currently something divided by the square root of C naught. So this is something divided by the square root of C0. And that's turned out to be working here. But yeah, that's a matter of moving it up and down. But okay, it's close here. It's reasonably close here. But yeah, no, this is not good. How should I change this? Seems the red one is actually better. Too low, maybe too low here. Here is better. I need something with a fractional alpha, fractional exponent, I mean. Maybe. I think that one is really neat. Now it's more or less everywhere the same distance below it even. Let's use this one. Okay. Anyway, let's go back to 0.2. Ah, brilliant. Now I need something that is a upper bound or a lower bound. So this noise here, each dot is accurate, but depending on the bits, even I mean, this is C naught, right? But yeah, it's a double, so it's, even though it's I don't know here, even though it's around this value 3.3, say, it depends on the fraction. If you are high or low in this band. So it's literally digital noise. Floating point round-off errors. That's what you see here. But okay, for whatever value here is, if you're above it, it's going to take 3 iterations. So I want to have the relative error, it must be smaller, aka below this. And I'm going to aim for even being below below this graph, which is ridiculously too far down, but hey, that's probably doable, so why not? If it's not doable, then we can always try to move it closer. But here, for example, you see, well, you probably don't see it, but there's a single dot here, my mouse is pointing it. So there are outliers that require this thing to be this low. Here as well, there's one outlier here. So it's good to have a pretty safe distance from it. Now this is for C naught plus 3 times x plus x to the power 3. Calculating the root of that. And I also need it for the one that I already did, because as you can see, this is a major improvement over what I had. I completely rewrote Halley iterations. How many viewers do I have? I can't see it, but if I have more than 4 viewers, I'll explain to you how this works. 6, wow, you're lucky. Okay, but I'll explain it. So we have the following cubic, where C naught is larger than 0, but can have any value. And C1 is either plus or minus 3. And we want to calculate the root of that. the root being the value of x for which this thing is negative. And of course, if c1 equals minus 3, it may be minus 3 or plus 3. It's minus 3, then the shape of this cubic is going up, down, up. So it could cross the x-axis 3 times, but we're only interested in the smallest root of that. And it's centered around, I mean, the inflection point is at x equals 0. So let's say this is the y-axis, then it goes like and then crosses through the y-axis and then goes like that. So this root is always negative, the smallest root. Now we can write the relative error of some guess that we start with as that guess minus the actual root value. Of course, there is a value of x here for which this thing is exactly 0, assuming that the doubles are exact, even though they are not, but we just interpret them as having an exact value, then there is an exact root. And we can make a guess for that root. And then the relative error in that guess is the difference divided by the absolute value of the real root, which is, I mean, I swap these, so there's a minus sign, and then divided by r because of that, because r is less than 0, which I just pointed out. Whether or not it's plus or minus 3, the root is always negative. So we can write that knowing the relative error in R0, we can find R0 if we have the exact root. Now, after having this R0, which is the initial value that we are going to use to approach R using a Halley iteration, so it's kind of the same as Newton iterations, but then also using the second derivative. Then I want, the comment says 1, 2, or 3, 1, 2, 3, or 4, but I already decided, or it's already clear that we have to go for 2 iterations. So we do this, then we do twice the Halley step, and then we want to have found R with the precision of a double. And then the question is, how bad can this R0 be? So that after 2 iterations, we still have the best possible R. We just found it after 2 iterations. You can't go very wrong, but you can go a little bit wrong. Like 1% wrong from R, and then 2 iterations, and then you have 18 digits precision. So Halley is very fast, very good. Now we have the following functions. The first function calculates the root given C0 and C1, and this is the exact root. I'm using a multi-position reel, 128 bits in my case, but I could make it arbitrarily precise. That's not necessary though. And then depending on if C1 is plus 3, then we just take 0 as a starting point. Otherwise we take minus the square root of 3 as a starting point in order to end up in the correct root. Only in this case, of course, there are possibly more than one root. And then we do the Halley iteration. This part is the Halley iteration. And we do that until either u was not changed at all anymore, so the step became 0, or the new u after this iteration is equal to the previous u or equal to the previous u. And the last thing must be done because it is possible that it never becomes stable and it never becomes this, and step just alternates in sign. So we overshoot and then undershoot, overshoot, undershoot, overshoot, undershoot. That means that it takes 2 steps before you return to the same value. And if that happens, you might as well stop. And then we return U, but this is with a precision of 38 digits because 128 bits over there. So then I have this function, exact root, which just calculates the root at 128 bits and then converts that to a double. Well, that is then 100% the best double you can wish for. There is no representation in a double that is better, for sure. So this is the exact root as far as it fits in the double. Now we have this beautiful function, which counts the number of iterations that it takes. Well, I'll read the description here. Returns the minimum number of times a Halley iteration must be performed on initial guess, which is passed here, in order to reach the root of that cubic as close as possible. Where as close as possible means that an additional iteration does not improve the accuracy. Yes, so let's say we do it one time iteration and another time, and it changes and it gets better every time you do it. It gets better unless you get this at the end overshoot, undershoot. Then it doesn't get better. But that's the only other possibility. Otherwise, it gets better. So it gets better and better every time it changes. It gets better basically until at some point you do an iteration and it doesn't get better. Then the last iteration was not necessary. So we just count the number of iterations to arrive at the previous one. The number of iterations that were actually necessary to reach, that best position that we could reach. This is done as follows. We set U to initial guess. Yeah, so this is going to be a function. The number of iterations is a function of the initial guess, of course. So these are fixed values. So in the graph horizontally, also C0 is now fixed. And C1 is still either -3 or +3. And then we just have some initial guess, and I want to know how many iterations. Now what you do is, if the initial guess is already exact equal to the correct root, which was calculated with the exact root call here, then of course the number of iterations equals 0 because, you guessed it right immediately. Otherwise, we are using standard nextafter, which returns the next double that is different from the one that you pass here, but for the rest as close as possible. So basically you add one bit. The least significant bit is incremented or decremented, as it were. And we do that in both ways. This is just a direction, so we go towards plus or minus infinity. But that infinity is a bit bigger than the step that it actually takes. So we go for double resolution steps, bits, whatever you will call it, in both directions. And if one of those equals the correct root, then we have a count less than 5. Otherwise, the count is 5 because we then just exit this for loop. And 5 is called a large count. We will always get as close as 2 even. But okay, so there's no need to count further than 4. Now, if the previous count is not still large and the current count is greater or equal to the previous count, so ignore this for a moment, then there was no improvement at all, right? I mean, the count is the distance from what we reached, the current U value after the last iteration. The iteration follows here, but even initially we have 0 iterations. So the number of nextafter calls to reach the correct root. So this is a really tiny distance. And then we have 0 till 4 steps like that. And if the number of steps is greater, well, that's not going to happen actually, but why not? Or let's say the redis is equal. If the number of steps is equal to the previous count, probably in the opposite direction, therefore. So you have an overshoot and you are at a distance of 1 step down, and then you have an undershoot. Then you are at a distance of 1 step up. So in that case, both would be 1. And then they would be equal, and then we stop, because there is no improvement. However, I added a -1 here, because if you don't do that, and you really go to the absolute maximum accuracy that you can achieve, then there are certain bit patterns, most not, but some bit patterns for the initial value, the double of the initial value, that for some reason, due to floating point round-off errors during this calculation, just require one more iteration step. You just, for some reason, just can't get that last bit unless you are already there. So it takes 2 steps to get very close, but not as close as possible, and then one more iteration to fix the last bit. And I mean, if then I want to find the maximum relative error such that we need only 2 iterations, that basically means that in 1 iteration we already have to reach this almost perfect value, except for the last bit. And going from 2 to 1 iteration demand means that your initial guess has to be like 1,000,000 times more accurate. So this is just ridiculous. So we just have to do this. The -1 makes it, that the noise doesn't, that the noise has a lower limit or an upper limit, how you want to call it, anyway. Otherwise it just goes down. The noise is down all the way to 0, almost to 0. 1,000,000th of the 0 away. So then, nothing left. So I'm not going to go through a whole extra iteration step, which makes things slow, just to get that 1 bit more precision in that 1% that needed. Yeah, I mean, no. So that was my choice, hence the -1 here. I have a class where the class is constructed with the number of steps, the number of iterations that you want. Tolerance here is the absolute difference between the relative errors. I'm using a bracket algorithm to narrow down on the relative error. So if you go, the relative error is between those brackets, and if it is equal to the lower bracket, then you have 2 iterations, and if it is equal to the upper bracket, it's 3 iterations. Now, if you bring these 2 very close, then of course you have found that border where you're very close to 3 iterations, but not. Okay, now this object has a function called iterations, which is passed a relative error, and of course the polynomial and the real root, although the real root is a double, so it's not super close. Doesn't really have to be that accurate, because the only thing that we use it for is to calculate the initial guess. Well, maybe it should be reasonably accurate. Actually, I think I'm passing it I'm passing the most accurate value as well. But, well, we just use it here to calculate the initial value with the given relative error. And then that is passed as initial value to iterations, which I just talked about. And then this member function, maximum relative error, And this is basically the same as this one, but then we don't have the relevant error yet. We just set the minimum, the relative error for the minimum to 0, which means, well, relative error of 0 means that your initial guess is exact, so the number of iterations is going to be 0. And the maximum relative error is just insanely large, or very close to very close to the maximum of the curve, which means that it also takes a lot of steps to reach the correct root. And so there's definitely more iterations than 2. So the first time you get here, this is going to be 0, and this is going to be more than 2. And then we say, as long as they are far apart, those two relative errors, well, they are, because one is 0 and the other one is 10 to the power 10. We halve it, and then we move the bracket that can be moved. So bracket algorithm, and then in the end you just end up with 2 relative errors that are very close to each other. 10 to the power minus 9 close to each other. Where this one still has 2 iterations, and that one, which is a tiny little bit larger, has 3 iterations. And we do that for both poles, being 0 and 1, which means that what is the difference? There should be a difference. Yeah, of course. The initial values of the rel r and this one is 0 in both cases, but the other one is either minus 10 to the power 10 or plus 10 to the power 10. So it's a positive, or it's going to be the sign of the relative error, positive or negative. And well, we'll just return both. It's an array of the both of them. And then finally, well, we make this graph here, and I just run over all the C0 values with a small step, and then we draw dots at the calculated relative error positions, which are calculated by this call. It's a function that we just talked about above. And well, this is for plus 3. So if I change this in minus 3, then we do this exact same thing, but then for the other. Clement says, and you don't want the divergence? I don't understand what you mean. Divergence of what? The divergence of what? Well, yeah, and I mean, it's not continuous, but we're going to use an approximation. For that, I need a mathematical formula. I'm not gonna manage. Actually, I would not need a mathematical formula. What I could do is run this code to find the value for a certain value. But I mean, if you change the double just one bit somewhere in the least significant bits, then it jumps up and down already. So it's very sensitive. So the only way to make sure then that we would stay within the correct bound is by testing maybe billions of values, I think. Well, you have to scan a whole range of possible values. So in the end, we're going to get an approximation to like a polynomial of a function is approximated with a polynomial. So you get an error function that goes up and down like this. So it's like sinus-like or parabola-like approaching a certain value. And then at the peak of it, it should not go over a certain line because then it's too high. But that line is my continuous function at the moment. So if that line becomes super noisy, then I have to test every bit resolution of the double as soon as we are close enough. So say the noise is as wide as as this here, let's say 4 lines, and our approximation comes here. Then at this point we enter the noise. So now it is possible that it goes wrong. So then you have to check over this whole range. Over this whole range here. That's all the time that we are inside of it. For every possible bit combination of the double of this whole horizontal range, I would have to determine what the number of iterations are, which would be very, very CPU intensive. So instead of doing that, I'm just saying, I'm just assuming, I'm just approximating the noise by its lower bound and then draw a straight line, and then the only thing I have to test is one point, namely the tip of my approximation. Yeah, I want a continuous curve thus, for that reason. It's not super necessary, but it saves a factor of 1 billion in CPU time or something. Maybe we are approximating anyway, so it doesn't hurt to approximate a little bit more. -3. That's what I use in the old one. Let's use that here as well. So far all this code is now usable for C1 is plus or -3, both. Except, I think the code in main. No, it was -3. Oh, there it is. This range is actually more something for the -3 thing. Even that. Should test it. Yep, we're going to test that. Now this function of course as well, so let's just remove it for the time being. No function at all. Well, no function at all doesn't work. Let's add an empty function again. 0.0. And then no, that should do it. Basically, I want to figure out this graph, but I'm also not sure about the range yet. But that was for the other one. So at the moment, I don't know. Keep the same range. No idea. Shocking. What the hell? Yeah, I guess the reason is that in this case the square root is minus the square root of minus it's minus the square root of 3, the root, so it's not 0. And here of course it's larger, but all in all the root value itself is more or less the same, so it doesn't change super much. So the relative error in it is more or less equal. It does slowly grow though. This step at 2 is so interesting. I wish I understood where that came from, but I don't have time to investigate that. Okay, so we're talking about... okay. I meant 0.02. 3. It's more like that is the correct range. And this is also the correct value, I think, because anything larger than this, we will just approach with... can add it. This is more or less constant then. So what is so special about the value of 2? What the hell is so special about the value of 2? That exactly there we have this sudden increase in allowed yeah, probably it's just we get one more bit accuracy maybe at that point. So I want to draw a line here maybe. Meanwhile I'm at it anyway. Yeah, it's not very important. Treat it like a constant. Or you cannot treat it like a constant. Okay, let's say at 0 you are at halfway here. Maybe even 30. No, that would do it this way. Yeah, halfway. 0. 0.0125. And then I want to end at the end at... Maybe not at the end, but at... oh, this is a good jump here. So let's go like that. No. Let's say at 5.5 we want to cross this. Just nonsensical. It's more like a problem. No, it's a straight line. Here it's a straight line. It's a straight line with a kink, and then another straight line. Now I think about it. At the moment, I'm cutting the thing into like here at 0.903, and then end up with a polynomial that's like 10 times more accurate than the approximation that I have for above that. So maybe we should go for cutting it at 2. And then I can just approximate this part with a straight line, and then that part separately with another straight line. Do first the first half. I know, I'm just going to gamble it, I think. Oh boy. No, just blackouts. Unbelievable. Zero, 1, 2, 5. That's what I wanted. Yeah, plus something times C naught. I have no idea. Not that one. Not that one. I was going to do a binary search, but let's do a decimal search. Oh, wow, yet in one. Almost. It's a little less even. A little bit less. How much less? A little bit less. It's probably too much. Not too much. Hmm? Hmm? Come scary close. Well, it's good, I think. Plus, I should only go to tilde 2 horizontally. Horizontally, we go to the 2. What am I talking about now? This one is 0. No, it's 1. What? Oh yeah, right. Still 2.0. Yeah, okay. Okay. Just not okay. It's too slow though. Too slow. Oh, I finally understand. I said 10 times. No, let me get 100 times faster. I was just shifting. This is 4 times as fast. Oh, it was confusing. 2 and 10. Okay, let's stick at this. Let's also draw a line here. And that would be the negative of this. Put the parentheses around it. Yeah, interesting that the distance is definitely larger, really. Really. Hmm. Yeah, it is. Yeah, I first need to write this to write my neural network though. It's closer than the other, I think. No, I think I like this one. And then I need a line for Yeah, I mean, there is of course a softer way to solve this instead of trial and error, but I wonder what is faster. I think if I just do this by eye, then it's kind of boring, but in the end, it's going to use less time. So this isn't a super close, so I might as well rotate it maybe around this point. Let's say 5. So I want it. Yeah, let's rotate this line around 5. Which means that the value at 5 is correct. I'm saying rotate it around 5, and how do you do that? Am I rotating the thing the wrong way or what? Rotating it the wrong way. Very good. And then we do the one at the bottom. Let's first calculate this. Excuse me. I think we're gonna make this a 4. Actually, wait. 5 to 8 was a 3. Okay, let's make this a 5. No. Macros, yeah, to have no code duplication. And just abuse the same code, the same file rather, yeah, and thus the same code for more or less different things. but enough the same for not wanting to make a copy of the file and then make changes. I think it's beautiful. It's beautiful. So that's for the -3 case. And then we are done if the +3 case is still working. Or you're talking about my debugging library of more than 20 years old. I mean, not that it's too old, but that it is tested by time. It feels like that this one is just numerically unstable. I should use a different Halley method. You can see that, for example, by the big outliers here. This kind of noise. Noise is like way more wider. Thick outliers, like super low outliers here. That's why I have to stay at this distance. Shrek, I think it's by now PhD level, thesis level stuff. I'm just doing research. There's no way you can drop in and then understand it. You can understand if I explain it, but even then you might take an hour to really study it before you understand what this is about. It does remind me about my time at the university, and you're also, just hacking away, trying to reach a conclusion that you can draw that sounds sensible. Yeah, what shall I do? I think I'm just gonna stick with these things, really. I could make them closer, bring them closer and stuff. I could even split it horizontally in parts, like I did with the other. Just now cut it in two with the other. Cut it at two, sorry. So if we cut it at two, then I could just approximate this one with a curve that goes like this. But in the end, I think, and then this one with, again, a curve like that. That would be pretty cool. And then here I had to cut it at 3 as well, apparently, or a little bit beyond 3. Have a curve like this and a curve like this. But yeah, like I said, I don't think it's going to make a difference, really, in the end, for the polynomial degree. In the end, I just want to have an approximation in terms of CPU speed. The only thing that matters is the degree of the polynomial that I need to make my approximation. And if I can, let's say, with a polynomial of degree 3, stay below this line here, which I draw with my mouse, then it really doesn't matter that you stay below this line. I mean, yeah, no, we're just going to stay way below it anyway. And then let's say with a polynomial of degree 2, hey, we save a whole multiplication, but probably just stick through the noise here anyway. So yeah, this, I'm going to stop here, I think. There is something important though, what I need to know for this case. And that is the cutoff. I do need an interval, otherwise I can't approximate my... I can't fit a polynomial if I don't have an interval, and I can't go through to 0. So I have an approximation for the root of my polynomial in the neighborhood of 0. And I also have one for going to infinity. And I need to know at which boundary we can use that approximation. Which means that we have to draw a function in this graph that shows the relative error of those approximations, which is then going to be 0, no error at all, at 0. So there's a line here, and that's probably going to explode. I think it's going to be horizontal and then explode almost vertically, and then cut through the noise here. And then where it cuts this function, we have our x-coordinate. So it's the beginning of the interval that we want to work with. So the question is, what is that function? Good question. Let me think. Good question. I think it was something with 81 in it. And I might already have written code related to it. I'm just going to search for 81. Yep, there it is. Plus 3 case. We are working on this. Okay, maybe this is for the... I can't remember it, but maybe, you know, just run it. Yeah, that's the one that I want. Yeah, that is the relative error of the initial guess as a function of C0 using that formula that I just showed. So this exact graph we want to draw in the other one. And that is plus the plus 3 case. So let's have a look at that. Plus, the plus 3 case, and now you want to copy that to the Halley iterations 2, which, yeah, we'll do that. So that would be this one. Relative error to double. Relative error is root 0 minus root divided by the absolute root. Just literally. Okay, and that is then root 0 is the approximate root, and the root is the actual root. That belongs to C0. Okay, so it's as simple as that. Double is precise enough. I can just copy this, I guess. but I don't have those functions. Okay, so add function, add function, add function, add function. Let's add that one, but only for the +3 case. Yeah, that's a +3 case thing. And this is called graph. Add function to plot the relative error for the approximation of root 0 near 0 or something. Yeah, I don't need to go through MP real here, I think. So let's just do double root is exact root of C0. And the root 0 is approximate root of C0, and then the relative error is root 0 minus root divided by the absolute value of standard root. Standard absolute root, I mean. And I don't need to print this. And this is already doubled, so I can just return it actually. An exact root is part of this file, right? Just yup. And approximate root needs to be copied, so that would be this one. Code duplication. Actually, yeah. No, the C1 is always the same here, but that's why I don't have to pause it here. That's even better, I guess. I just paused 3.0. That's amazing. So we can use it almost till 2. Wow. Almost till 2. And because it goes up here, we can just use it till 2. And you know, this is a big space here to... Oh my God, look at this. Wow, because, oh, That is really, 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 really interesting. My mouth drops here. That's exactly the path that it follows here. So we can use it because it goes up here and stays above this line for some magical reason. We can use it all the way up till 3 point something. And all that time is going to be just 2 iterations. Well, except on this side. For this side we need to stop sooner. Maybe I'll just do till 2. But it is, yeah, this so that, why? So this line here, this line represents the second order approximation of the root in terms of C0. Second order around 0. So it is very accurate at 0. C0 is 0, it's very accurate. And it is second order, so it stays totally 0 for small C0. But if C0 becomes larger, then of course it's not accurate anymore, because it's something like C0 to the power 3. I think C0 to the power 5 is the next one that you should add for as a correction term. And then you see that it exactly follows this line, where this noise here, it's I mean, really, I had no idea where it came from. So how are those two things correlated? So intriguing. I need to draw it down as well, though. So do that first. So I'm a bit confused. I'm going to just add a minus sign here. But what does it mean? Relative error is what it is. This. That's literally the definition of relative error. That can be negative too. So what I really should do is change this formula. Just a different approximation, really. Sorry, this is not good. this must be need a different type of approximation then. But what? Smelly, yes it is. Totally. But not the code that I'm working on right now. This is a new file which I didn't, well, started it today. But the whole project is on the GitHub, sure. I'll give you a link. If you want to compile it yourself, you just have to use machine learning, I'm afraid. Because what you need is the math directory and the Cairo window directory. Yeah, and CWDS and CWM4. And utils. Especially because of math currently, you really need to use the machine learning one. And then if you want to compile it, you might run into error problems, but there is a description on how to compile it, which it's easy if you have Arch Linux. Otherwise, you might just have to tweak it a little bit to avoid needing TensorFlow, because you don't need that for the Cairo window. And then inside the Git submodule Cairo window, you have the tests directory. So I'm usually inside here, Cairo window tests, and that is all the test stuff that I'm working on right now, which does stuff like open a window and then draw something, and you can drag points if you want. Well, yeah. So it kind of demonstrates, the code demonstrates how to use Cairo window itself, these tests, but they actually test something that I was adding to the library itself. So I think this is one of the first ones, just simply Cairo window. So nothing can be dragged yet. Just a picture of the construction of a rotated parabola, which is a Bezier curve. It's quadratic Bezier curve, I guess. Yep, so I just wrote this one, and we're working on the I think these two, yeah. So this one is finished. So I'm working on this one, and for that I need information that I got from this file now. I'm still missing something though. It's just I just started this, so it would be better to run the other one, which is finished. So let me. So this is the green one is the polynomial approximation of the black thing here that we eventually arrived at during this derivation, which ends in, because it just very quickly approached it, This is the final polynomial, this one. Which then has a minimum and maximum deviations. So the deviation is from 0 to that, and both up and down to the red lines at the same distance, and it touches here and then again there, and here and here and there. All these points are at the same distance, and then between this and that interval you have the best second-degree polynomial approximation. Yeah, you should just look at the file, I guess. The -3case.cxx, very mathematical file. Okay. I think I'm going to stop. My brain is clearly starting to run a bit empty. Yeah, I need to add another one here. Approximate root. Call this approximate root. I don't think what the difference is to begin with. It's the difference is the sign of the relative error. And what we got was positive. So call this plus. Gonna need a minus. Now let's. What shall it be, right? There is no other. It's just a coincidence that it is positive. There's no other. It's just nonsense that I change this. Not even drawing it. That thing is just the best approximation, but and it also has a positive relative error, period. So we don't even care about the negative ones. Okay. Now it is on GitHub. Well, not entirely. Still have to push the math one apparently. I should not remove the fix me, I think. Okay. Now it is all good. You can pull machine learning and you get the latest Cairo window as well. Well, pull recursively, that is. AKA run autogen.sh in the root of the project. I think that should do the trick. Lightjes. Okay, let's play a game of chess. Why do I play something with 2061 question mark? I guess I should have taken it. Playing the f-pawn is like really bad. You could play this pawn. It's first gonna take. Let's play this pawn and it threatens check. Yeah. Double attack here and this check. If I play up the pawn, it just takes here or check and I lose the rook. So this is already kind of a double attack. Can still stop it with this, but then the bishop comes. No, the damage is not that bad. I just have an isolated pawn now. Yeah, he does it. Never play f3. I know. He's a funny guy, this Feingold. Guess this guy got a point. You can go here, he just castles. And then I'm standing here. No. And then what? Well, then I can play my bishop here. I'm taking the rook and that one, so he has to take. And then I take back, and then I'm threatened to take his other bishop as well. Well, too threatening. There's no bishop pair left anymore, so maybe not that bad. But my knight here cannot be chased away easily. And it prevents a rook from coming here, so he's gonna have to do a lot of moves. I think I'm gonna try this. Or he could play maybe this, threatening to that. Is that bad? No, not that bad. Let's do this. It's kind of a monster of a knight that I get now. See, he doesn't even want to take it. And rightfully so, because if I take his bishop, he just takes back, and then this one is developed as well. Way better. Now he's going to chase my knight away, of course. Don't you wish you could castle? Whoa, attacking my bishop again. Yeah, that's true. Okay, I'm just gonna take it. Oh, the moment I click it, I see that he attacks it 3 times. Ah. I could have done something about it. I could have moved my knight back and just defend the pawn. Shit. Yeah, can put a rook behind it maybe. Yeah. You take with the knight, I take. Just take with the other knight. Can't give check. I can attack it again. And then he has to move the knight again. But yeah, you can just go there or there. Even if I take, it just develops. Pretty much sucks. Unless, let me think. Check, 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 check. No, it's a piece. Shit. It's the best I had, I think. So I'm trying to take here, and then he can't take back because the gift mate. And if he develops the bishop, okay, it just moves the knight. The solution was simple. Okay, I'm gonna go here. Threatening mate again. Don't have much here. Really? Oh my god. Yeah. Really, this is just to be expected, I guess, against a high-rated player. No, give up. Bah. No, maybe not good. I don't know. Well, I pin the rook if I take the queen. Yeah, he moves the queen. Okay. But now this one is a bit... attacked, as it were, almost. We should just go here. Not a very nice move, though. But need to take there and there, will that matter? Do I really want to do this? No, I don't. I really don't. Just do it. A bishop had to move anyway. And it attacks a knight. That looks like a completely free bishop. I think I'm gonna take it. That's why the rating is so low of my opponent, of course. 19. Oh. Oh yeah. I don't want to go to bed. There's a song like that. There's a song about not wanting to get out of bed. I'll play one more. There's always one more, isn't there? Not that again. What is my bishop doing here? Why? Is this pawn that important to you? 1, 2, 3, 4. I'll aim my pieces on something else, I think. Just kick this thing because I can't move my knight otherwise. This one or this one? I don't know. I should not be scared and just castle. Yeah, I want to play this pawn to stop the bishop from coming here, but on the other hand, you might as well sacrifice his bishop on this pawn then. Queen here and then take it. Unless... I could have just taken it. It was a free pawn. Take it. Pawn is a pawn. Yeah, that was not a bad move. Not a bad move, this guy. He threatens even to take here. No, he can't give check then. Oh man, attack. I could take this pawn. Why did not just take this pawn with threats? Take other pawn and fork. Ridiculous. I'm gonna go back. Let's try that again. Yeah, no choice. And now I'm gonna survive that or not. Go here, he goes there, I take here, he threatens mate, play my rook, give check, go here, give check again, I go there. I escape. Probably not. Or no, he doesn't, not two moves, he goes there or there. And then is mate in one threat, so I have to play this pawn. And then he goes here. Whoa. Play rook, check, mate. That's not good. Wait a minute, if he goes there, I just take the knight. Okay. Unless he takes my... So, okay, take. Threaten mate in one. I'm gonna do it anyway. He's going there. Now maybe he wants to go there. Okay, I'll just continue taking stuff. And then the idea is that I survive this, right? That was the idea. If I calculated everything correctly, then I will survive this. Threads made in 1, absolutely true. And threads to give check here. But then I just go here. And I could still keep my pawn or not. Suppose I run immediately and it just takes it with check. I put that there. I could then theoretically take, yeah, I think I'm just gonna defend it. That is not going to work. I'm just going to go here. Interesting. Check, I go there. Check, 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 check. Infinite check? Damn it, I don't have time anymore. I don't have to take back though. Could just take the queen. So he has to start with giving check, and then I just defend this. No. I have to keep defending my pawn. Whoa! Oh! Fuck! Don't tell me I'm dead. I'm dead. I am dead. Yeah. Oh, maybe I'm not dead. I'm pretty sure I would have been dead if he had moved the right move. Move the knight. Okay, I take this one. Take my knight. Oh, it doesn't do it. No, I guess I need to protect it. Protect the knight. Exchange. I have no time left. No time whatsoever. A rook here, easy enough, no? What would I do? Well, that's one thread less. Hmm. No, I had. He could have won my queen. I don't know what I'm doing here. It's just nonsense. There's no bloody time left. I need more space. Oh. Fuck. There. Oof. I should not have done that. Then again, no time. Yeah, next time I just go there, right? Of course, I go get my knight out of the pin. Yeah, repeat moves because you're running out of time, man. You are running out of time. Yes, repeating moves. Let's develop my knight. Yeah, that's possible. Okay, let's check. Pawn. I don't know. Nothing is good, really. He's pretty scared to... Oh shit. Oh shit. Oh shit. Yeah. Oh well. Let go. I'm so going to bed. So going to bed now. Yep. Good night, people.